Yes, doctor.
Okay. First, what we need to do, so we need to, I think it's good if you can use a picture, okay, so that you can draw something to represent your situation, the condition. So, then from there, you can do the calculation. So draw something to represent your system, okay, so that at least you have something to refer to when you start to do the calculation. Okay, so from here, you see, so this is what I draw. Okay, actually it should be like this, right? Okay, we ignore this first because this is for another part. So initially we have two plates, plate 1 and plate 2. Okay, so plate 1 temperature is 800 Kelvin, emissivity is 0.5. Plate 2 temperature is 400 Kelvin, emissivity is 0.8. Okay, so part A we have already discussed. So just now your friend already discussed the solution. So it's exactly the correct way. The way she explained, she analyzed also very clear, very good. Okay, so just now Amino also showed us his solution. So I think he also did a good job in terms of presenting us the circuit diagram of the problem. Okay, so it's good if you draw something like this, then after that you construct a circuit diagram to represent your problem. So there are altogether 3 resistances. Okay, 1, 2, and 3. So R1 is the surface resistance of surface 1. Then here is R2, surface resistance of surface 2. Here is normally we call, you can name it R3, or some people name it as R space resistance between surface 1 and surface 2. Okay, then after that, so I think a good solution will provide first this diagram. Second, it will provide the circuit diagram. Okay, then next slide. Okay, so this is the chart you use. You refer to curve number 4 since it is a long narrow rectangle. Okay, I have a question here. What if the dimension of the rectangle is 2.5 times 1? If it is 2.5 times 1, so which curve you need to refer? Any answer? Instead of 3 times 1, it is now 2.5 times 1. So which curve should you use? Just unmute yourself and tell us your answer.
Curve 4.
Curve 4, okay, is correct. Okay, because it's still considered a long, narrow rectangle. What if the dimension is 1.5 times 1? What if the rectangle's dimension is 1.5 times 1? Which curve? Okay, I want you to type your answer. What if, my question is, what if the dimension of the rectangle is 1.5 meter times 1 meter? So which curve should you refer to? Okay, type your answer there. Four also. Still curve 4. All of you say 4. Any other answer? If I were you, I would choose curve 1 or curve 2. Okay, you can still see my slide, right? Okay, you see, curve 1, sorry, not curve 1, it's curve 2 or curve 3. Okay, I think curve 2 or curve 3, both can be considered correct, because now you see your dimension is 1.5. Okay, 1 times 1.5. So which one is closer to this? I think square or 2-1 rectangle. I think maybe 2-1 rectangle is better. Okay, as it is closer. If I compare to long narrow rectangle should be, if the length is at least 2 times as compared to the width, because now you have a category of 2-1 rectangle. Okay, so 2-1 rectangle. So if we have this, the dimension is 1 times 1.5. I think if I were you, I would categorize this as a 2-1 rectangle instead of a long narrow rectangle. Because if I were to categorize a rectangle to long narrow, it should be longer than 2-1 rectangle, meaning the length should be at least 2 times as compared to the width. You got my point? So I think curve number 3 is a better solution as compared to curve 2. Because curve 2 is for square, and since this is not a square, so to me, if I were you, I would choose curve number 3. I would categorize this as a 2-1 rectangle instead of long narrow, because the length is not at least 2 times as compared to the width. Okay, so let's move on. Okay, let me clear this. Okay, let's move on to B. Okay, so this is my solution. Amino, maybe you can compare my solution with yours. Okay, so actually it's a straightforward solution. We use this formula. This is a formula for two gray surfaces. Okay, so actually epsilon 1, epsilon 2 are all given. T1, T2 are all given. Okay, all these are given. Okay, then A12. So A1, you can also calculate. F12 you determine already 0.62. So what you need to do is to substitute all these values into this equation. Then at the end you will get the answer. So this is my answer. Okay, let me show my answer. Okay, class, you need to know how to name all these resistances. So here, okay, first, this is the original condition. So we have three resistances. That is, okay, so resistance number one is surface resistance of surface one. Resistance number two is surface resistance of surface two. And resistance number three is space resistance between surface one and surface two. Then after adding one aluminum sheet in between 1 and 2, let's name it as surface 3. Then the new resistances added, okay, there are 4 actually, because now altogether there will be 7. Okay, the R space originally exists between surface 1 and surface 2 now no longer exists here, because surface 1, surface 2, between them now is surface 3. So R space original between surface 1 and surface 2 no longer exists. Okay, but there are 2 more space resistances between 1, 3 and 2, 3. So these are the 4 new resistances. Okay, one is resistance due to the space between surface 1 and surface 3, 1. So this is surface 3. So you have surface 3, 1 and surface 3, 2. It normally is like this. Is 3, 1 and 3, 2. 3, 1 because 3 facing surface 1. 3, 2 because surface 3 facing surface 2. So you have one space resistance here. Okay, and 2 space resistance here. Okay, and you also have surface resistance due to surface 3, 1 and surface 3, 2. Okay, so these are the newly added resistances. 1, 2, 3, and 4. 2 space resistances and 2 surface resistances. Okay, I hope that's clear. Okay, this is my solution. So the basic principle is Q is constant. So that's why Q131 is equals to Q12. Okay, Q, if you see this situation, okay, Q12, okay, Q12, this Q12 is the same as, so the first one is Q12, the second one is Q13, 1. So they are the same. So based on this principle, so we can solve this problem. Okay, because we know what is Q12. Then by using this formula, then substitute all these values. Then at the end we will get what is T3. Okay, my answer is 678 Kelvin. So that's the answer. Okay, so that's the end of this problem. Okay, any question so far? Any question you have?
Doctor,
Yes.
may I know for the question D, right? It says a aluminium sheet is added. My answer is different because I assume the aluminium sheet is added in between the two plates, so the distance become 0.25, which makes my F13 and F32 different with the first view factor.
Okay. I think you are right. Let me see. Yeah. What 29? Okay, 29. Wait. Okay, you assume 13. Okay, let me check my 13. Oh, okay. Yeah. Okay. So meaning your solution, your F13 and F32 is different, right?
Yeah,
Okay, it's no longer 0.61, right?
yeah, I get 0.76.
76. Okay. Did I mention in the question what is the distance between plate 1 and plate 2? Given,
Doctor,
right?
you mentioned the distance between plate 1 and 2, but after adding the aluminium sheet, the distance...
I didn't mention.
Yeah.
Okay, so you assume the distance between... do you all see my screen?
Yes.
Okay, so your assumption is distance between, okay, initially is given 1 and 3 is 0.5 meter, right?
Yeah.
Okay. Yeah, I think you got your point. It's correct. Yeah, thank you for correcting us. Guys, the correct solution should be like this, because after adding shield number 3, okay, then actually the view factor changed already. Do you realize that? Because your assumption is plate number 3 is exactly in between 1 and 2, right? So the distance between 1 and 3 is 0.25 meter, right? And
Yes.
same goes to this. So because the distance in between 1 and 3 changed already, so view factor F1, 3 and F3, 2 also change. Okay, F13 and F32 change is no longer 0.61. Okay, so 0.61 is wrong because now the distance between them has been halved. So when you use this graph, okay, when you use this graph, instead of 2, here it should be 4, right?
Yes, I use 4.
Because x, originally it was 1/2, 0.5. Now after adding the new shield, the x becomes 1/0.25. So it becomes 4 instead of 0.25. So instead of 0.61, this original, now guys, it has been changed to this curve number 4. Okay, so it should be like this. So what you get? 0.7 something. 0.7? Sorry?
Yes, I get 0.76.
76. Okay. Yeah, because logic, right? If you shorten the distance between the two plates, then more radiation will force on another surface. So around 0.76. Okay, so you need to substitute this. Instead of 0.6, it should be 0.76. Same goes to this 0.76. So what is your Q? Now what is the new Q12?
The Q I get is 2988.25.
2988.25 watt. Okay, not much different actually. Okay, but the concept is your concept is correct. So yeah, I'm sorry guys, I made a mistake. So Supra, you also need to make some correction. Okay, is the wheel factor F13, F32 change already after adding the shield. Okay, so it will also affect your, is it going to affect your, yes, it's going to affect your T3 also, because now Q already changed. It's 298 something. So your T3 should be higher, I think. Yeah. Okay, any question on this, guys? Do you understand what I'm talking about? Who is that? Sorry. Who is the one who share this answer?
Me.
Who is me? I don't know.
Jingying.
Okay, Jing Ying, ah? Yeah. Thank you so much for sharing this. Yeah, your answer is correct. Yeah, very good. Thank you. So guys, do you have any problem, any question regarding Jing Ying's solution? You agree with, you understand what I tried to explain just now? Any question regarding this? Hello guys. Any response?
All good.
All good, huh? Okay. Okay, with that, if there is no problem, okay. Okay, if there is no problem, then okay, before I end, I want to give you one more question. You see my slide? Okay, the question sounds like this. The bottom of a steam producing steel, so this one, okay, 200 mm diameter, so you are given the diameter of the bottom is heated by radiation. Okay, the heater is maintained, so you have a heater down here. Heater's temperature is 1000 degrees Celsius, separated 100 mm from the steel, has the same diameter as the steel bottom. Okay, so now the situation is you have two surfaces facing one another. Okay, facing one another. So if which curve you need, which graph or which chart you can refer to is this one, because this is radiation between parallel planes directly proposed with one another. Okay, but this case is this because you are given the diameter. So it's no longer rectangle or square, but is basically two circles. Okay, two circles facing one another. Okay, so the question is, by what factor could the vapor production rate to be increased if the cylindrical sides, okay, dash side, okay, this part, okay, were insulated rather than open to the surrounding, maintained at 27 degrees Celsius. So basically, there are two scenarios. Scenario number one, okay, scenario number one, okay, you have two circles, okay, and in between them, there is nothing. Okay, there is nothing. Scenario number two, so that's why you will have some radiation to the surrounding. But in scenario number two, you will have one insulation. Okay, meaning this part insulated. Insulated basically is, if you see this, okay, planes connected by non-conducting but re-radiating walls. Non-conducting meaning, insulated meaning that the heat will not be released to the outside. Non-conducting but re-radiating walls. So this is the situation, meaning the radiation will be reflected. Okay, either back to surface 1 or it will be reflected to surface 2. Okay, so you need to refer to different curve. Okay, this is curve number 1, this is curve number 5, I think. Yeah. So two situations, then you compare. Okay, scenario 1, scenario 2. Okay. Scenario 2, you have more heat be transferred to the steel. So if you receive more heat, meaning more vapor can be generated. Okay, so vapor generation, since it's vapor, so meaning what is involved here is boiling. Okay, it's boiling, but you don't need to worry about what we have learned in boiling, because you don't need to use that. What you need to use is, because what we are interested now is the steam generation rate. So what is steam generation rate? We know Q that is transferred from the heater to the steel is the Q. Okay. So this Q is Q. We assume heat only transferred from the heater to the bottom of the steel through radiation. Okay, instead of any other form. So Q is actually, so use the formula we have learned now. Okay, A sigma, then epsilon, then you have F1, 2, then you have delta T, right? You have T1, 4 minus T2, 4. Okay, and this Q is also the same as, because is what do you call that? The heat, this Q is used for one purpose only. Is used for producing vapor. So, and we have learned in previously, Q equals to, if involve boiling, M dot HFG. What is HFG? Is the latent heat of vaporization of water. This one you need to get the information from textbook appendix. Okay, so now first you need to calculate Q for both scenario, Q for scenario 1, Q for scenario 2, because they have different view factor. Okay, then from there you get Q for scenario 1, Q for scenario 2. Then you calculate with the same Q. FG you can get from appendix. Q you can calculate from here. Then you can get m dot. So m dot, the unit is kg per second, because your Q is what is joule per second. So FG is the unit is joule per kilogram. Okay, I guess you still remember all this. Yeah, then from there you can solve the problem. You can compare by what factor, meaning you use Q m dot 1 compare with m dot 2. Then from there you can get what is the factor. Okay, m dot 2 m dot 2 divided by m dot 1 times 100%, then you can get the percentage. How many percent increment for vapor generation. Okay, so I want you guys to try this, solving this problem. Okay, I guess the explanation is clear. Any problem, any question regarding this before we end?